diagram to you. So you see, this is the diagram. Now, what are the materials? What are the materials? You know, this is lead, and you know this is tin, right? Palubium, strontium, and so on. So this is lead and tin. So this is lead tin phase diagram. Again, there is temperature here. There is composition weight percent of tin here. So this is there. Now, can you find any triple point here? Any triple point? Just take 5 seconds, 10 seconds. Can you find any triple points here? Triple point means a point on which three phases coexist. Three type of different things coexist. So you see, let us see this point. See, on this side we have liquid. On this side we have solid alpha plus beta. Now, one thing which is very different in this diagram is this straight away. What is this? What is the difference? It is not isomorphous. Once it solidifies, there are two solid phases, alpha and beta. So it is binary non-isomorphous alloy system, right? Binary non-isomorphous alloy system, because when you cool it and become completely solid, there are two solid phases, alpha and beta. So this is one thing. But I was starting to talk of triple point and so on. Rather, forget about the triple point. You see, normally if you take any, say 48% nickel and draw this line and go from A to B to C to D to E, what is happening? Here we have only single phase completely liquid. Here we have solid phase alpha plus liquid. Here we have two phases alpha plus liquid, and here we have the complete solid phase alpha plus beta. So this is what normally happens. This is what normally happens from liquid to liquid plus solid to solid. This point is very strange. You see, just shift this dashed line to exactly the point, Here it is liquid. It is liquid, 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 liquid. No liquid plus solid happens. It suddenly changes to complete solid, right? So this is the unique point. This is the unique point. It was not there in any of the previous diagrams. We had copper nickel diagram, we have silver lead diagram. It was not there, silver palladium. Liquid always becomes liquid plus solid and then becomes solid. Here at one point, liquid directly changes into two solids. Here for this lead tin system, the composition at which it happens is 61.9%. It is written, right? 61.9% tin. And what temperature? 183 Celsius. 183 Celsius. So on a lead tin diagram, if the composition of the alloy is 61.9% tin and if the temperature is 183 Celsius, then what will happen? That the liquid will suddenly change into two solids, alpha and beta. There will be no normal change that the liquid first changes into liquid and solid, and then this very special point where the solid, the liquid directly changes into two solids is known as a eutectic point, and this reaction is called a eutectic reaction. Eutectic reaction, right? At any other point, if I am here, it is liquid, then it will become beta plus liquid, which is liquid and solid, and then it will become solid. If we are anywhere here, it will become liquid, liquid plus solid, and then solid, right? But here at this special point, it will become liquid to directly two solids. So this point is known as a eutectic point, and the reaction of liquid to direct two solids is known as a eutectic reaction, and this can happen on a phase diagram only on a special point. On this lead tin diagram, this happens at 61.9% composition and 183 Celsius. Okay. Now let us take the other example, that if we have a 40% nickel sample, a 40% nickel. Again, remember, 40% nickel means 60% tin. Sorry, 40% tin. I'm sorry, there is no nickel. This is a lead tin diagram. So sorry for my mistake. 40% tin, right? So right? So we just draw a vertical line. We just draw a vertical line. And then we will find at different temperatures, at a temperature of around 300, what do we have? We have point A, which means that what is the first question? How many phases are there? Only one phase, liquid phase. Second question, what is the composition of this liquid phase? 40% tin, right? That is it. If we drop the temperature until we just hit the line. As soon as we hit this liquidus line, some of the liquid begins to start to become solid. You see, there is alpha solid on this side, there is beta solid on this side. If you see, whenever there are two solid phases, then on one side, one solid will form, which is alpha. On the other side, the other solid will form, which is beta. So here, when you just touch this line, a very small amount of the liquid starts to become solid, and that solid will be the alpha solid. If we drop the temperature further, say this point, then more liquid has turned to solid. If you go to this point D, which is just above, right? Just above, it has not touched this line, just above this line. So say maybe 90%, 95% of the liquid has changed to alpha, but some 5%, 10% liquid is still there at point D. Once you touch point E, which is exactly on the eutectic temperature, this line, then suddenly whatever liquid was remaining has become alpha plus beta. Whatever liquid was remaining has become alpha plus beta. So this is very important. If you understand this, you understand almost everything in phase diagrams. So let me repeat. The example was that we have given you a 40 weight percent tin alloy, and we want to find what happens when we start to cool from a very high temperature to room temperature. This is the question. So we take a point A. First of all, of course, we draw a vertical line at our composition. We take any very high temperature point A. We know that there will be completely liquid phase and the composition will be only the original composition. When we drop the temperature until we hit and touch the line, as soon as we touch the line, a very small amount of the liquid has changed into alpha solid. When we reduce the temperature more of the liquid has changed into alpha solid, say 30%. When we go to point D, reduce the temperature further, which is very close but still above the line, above the eutectic line, then maybe 90-95% of the liquid has changed to alpha solid. And finally, when we touch the point E, then whatever liquid was remaining, 5% or 10% liquid that was remaining, that changes into alpha plus beta. After that, when we keep on reducing the temperature, nothing changes. Whatever had changed into alpha is still there. Whatever changed into alpha plus beta is still there, and that composition remains there, right? So this is it. So, right? So remember,